In section 4.1 of the text, you will find one proof of the Pythagorean theorem and several interesting problems to look at. We will do one proof of the Pythagorean theorem in this video, and two more we'll work on together in class or possibly as homework. Before we can do any of the proofs, however, you have to understand certain concepts about area, and so we'll start with that. As always, I hope that you will take good notes and write down the words that I use in this video so that you will be able to use them and recognize them on problem sets. First of all, we look at a triangle, a three-sided polygon. And let's recall some of the main things that you need, aspects of triangles that you need to know. First of all, these are called the vertices. So if I label points A, B, and C, these are called the three vertices of the triangle. I can use any side and call it base. I think I'll just use CB here, this segment here, as base. I write base. Or maybe it's just B, the length of the base. If I use this as base, then the height of the triangle is the perpendicular distance to the base from the opposite vertex, which is A. And we'll call this H, the height. We know that the area of a triangle is 1/2 its base times height. This formula is important. Another thing that will be important to understand is if we call the angles alpha, well, let me call this one alpha, beta, and let's say gamma here. It looks like this. We usually call angles lowercase Greek letters. We know that the sum of the three angles of a triangle is 180 degrees. So I could write this alpha plus beta plus gamma. The sum of the three angles of a triangle is 180 degrees. And you'll see why this is on a homework problem that you do or an in-class problem. Also, the edges here, these are called edges or sides, three sides to a triangle. Now, a right triangle has one angle that is 90 degrees. That's what it means to be a right triangle. This is 90 degrees. So if I call this angle, let's call the smallest angle alpha and the next one beta, we know that if this angle here is 90 degrees in a right triangle, that alpha plus beta must be equal to 90. Because the sum of the three angles is 180. And we know that A is perpendicular, that this side here, in fact, let's call those legs. These are called the legs of a right triangle, the ones that are perpendicular to each other. Those are the legs, and this longest side is the hypotenuse. We see that the legs are perpendicular and that the sum of alpha plus beta is 90 because this one is 90. And of course, the height here, the height of this triangle is A if we use this as base. So the area, which is 1/2 base times height, in the case of a right triangle, it is 1/2 the product of the length of the legs. So it's just 1/2 AB. That's the area of this right triangle. We need to know the area formulas for three different kinds of quadrilaterals. Of course, quad means four, so these are four-sided polygons. four-sided planar figures that have straight lines for their sides. One is a rectangle, the most basic, and let's say that we call the longer side L and the shorter side W, assuming they're different, and we would say that A is equal to length times width. Now notice that a rectangle has opposite sides parallel and all of the angles are right angles. So joining sides are perpendicular to each other. We also might note that opposite sides are equal. So opposite sides equal, all right angles, and these are things that you can assume are true about a rectangle. The area is the length times the width. Now a square is just a rectangle, but it's a special kind, and I'm going to call the length of its side S, and we know that all sides are the same. So for a square, the area is just S times S, or S squared. It's just a special case of a rectangle. The last four-sided figure or quadrilateral that we will look at is a trapezoid. A trapezoid has two sides that are parallel. And the lengths of those two sides you can see here, DC and AB. Those two segments are parallel, and we call the length of the bottom one here B2 and the length of the top one B1. Base 1 and base 2. We call these parallel sides bases. And H is the height. H is the perpendicular distance from one parallel side to the other. The perpendicular distance between the two parallel sides. So the area of a trapezoid is equal to 1/2 the sum of B1 plus B2. In other words, the average of the length of the bases times the height. Now, if you have a right trapezoid, that just means that you have this is a right angle here. So it's a special case of a trapezoid. And in this case, just like we saw in the right angle, this segment here, AD, turns out to be the height. So it's a little bit simpler. And we get the exact same formula for area. 1/2 the sum of the bases times height. You don't need to put this in your notes, but I'd like you to see why the area formula is what it is. It'll help you to remember it. The average of two numbers is somewhere between the two, isn't it? You add them together and divide by 2. So let's go from here, and let's see, B1 is this long and B2 is longer here. So the average of the two would probably be maybe from here to here. I'm just guessing, but that would be a little bit longer than DC, maybe more like that. Okay, that would be about the length of the average. And come up here and draw that same. And, whoops, and look at this rectangle. If this length down here, if the length of that rectangle is the average of the two bases, then this 1/2, the average of the bases times the height is just the area of that purple rectangle. And you can see approximately why that would be true. So the area of a trapezoid is the average of the two bases, the lengths of the parallel sides, times the height. And if we have a right trapezoid, the height is easier for us to determine because it's just the length of one of the non-parallel sides, the one that's perpendicular to the parallel sides. This next little theorem is just a name I made up to help you remember it. It's something that you know intuitively. but it's worth saying because we use it in all three proofs of the Pythagorean theorem. If you have, as in this case, we just have a rectangular puzzle here. We know that the area of the puzzle is the length times the width because it's a rectangle. But we also know that we could say that the area is the sum of the areas of the 10 little puzzle pieces. I just labeled each area as A1 through A10. There's 10 pieces to the puzzle. Now, we don't have a formula for those, but let's just say we knew them. We know that the area, the length times the width, could also be calculated by adding A1 and A2 and so on up to A10. So let's say this in general. The area of the whole is equal to the sum of the areas of its, its pieces. I'll put pieces since we're talking about puzzles. Okay, so this is something that you know, but keep it in mind because we're going to be using it. So let's state the Pythagorean theorem. We know that this is our 90-degree angle here. So we know that everyone knows it's a squared plus b squared equals c squared. But of course, a and b are the lengths of the legs of the triangle. And if you square them and add them together, you get the square of the hypotenuse. This is the theorem that we want to prove in section 4.1. Let's just jot down the area of this. We know the area is 1/2 AB, 1/2 the products of the lengths of the legs. Now, this is the triangle drawn just this way that we're going to use to prove the Pythagorean theorem. So on the next two slides, I'm going to make copies of this exact triangle. So the first proof, the only proof I'm going to do in this video is this is not the one in the textbook. This is actually my favorite because I think it's the easiest for you to see. I've made 4 copies, just cut and paste, 4 copies of the blue right triangle, and I have put them together like this. I've made a puzzle, and it has a square black region in the middle. So let's just label, you see this is A from here to here. And the long leg we're calling length B. And this is the hypotenuse here. And so let's just go label all of these. This is B, this is A, this is length B, length A, length B, A, and this is C, the hypotenuse, the hypotenuse. Okay, so I just labeled the sides of the 4 triangles, and we know that this is a right angle, so this is definitely a square because each side is A plus B. Notice up here I have A plus B. A plus B is the length of that side. So this is an A plus B by A plus B square. Therefore, the area, I'll do it down here. The area is equal to A plus B, the quantity squared, the length of the side squared. But it's also equal to the sum of the parts. So I'll change color here, and let's write the area of each part. This is the right triangle, so it's 1/2 AB. 1/2 AB. Here we have 1/2 AB. And the fourth one, same area. And the square in the middle, we should make sure it's a square. That has to be a right angle. But remember, the smaller acute angle here, the smaller one we called alpha, and the bigger one we called beta. And we knew that alpha plus beta, let's just jot this down up here, alpha plus beta was 90 degrees. So look at, this is a straight line here, you have a straight line, and this is alpha, and this is the larger, this is beta right here. And so if that's 90, if alpha plus beta is 90, and it's a straight line, then that means that that has to be 90 degrees. So this inside black region is definitely a square, and we can say that its area is c squared. So now I want to write the area in another way. This was the area of the whole and is equal to the sum of its parts. So we have 4 areas which are 1/2 AB. The 4 triangles plus the square in the middle, c squared. So this is saying that the area of the whole square, a plus b, the quantity squared, using the formula for area of a square, is equal to the sum of the areas of the 5 parts, 4 copies of the right triangle and the square in the middle. So what we'll do is just expand this out using algebra. If you need to review algebra, just come and see me or ask your teacher. Oh, in fact, I think I'm going to just review that over here. Let's just review how we expand a plus b squared. A plus b times a plus b. Remember, you called it in high school, I think you guys called it FOIL. So we multiply the first term, a times a squared, and add to that the product of the outer, a times b, and add to that the product of the inner ones, ab again, or ba, it doesn't make any difference, we'll write ab, and the product of the last terms, b squared. Well, this is 2ab, so we have a squared plus 2ab plus b squared. Now you do need to know how to multiply that out. So let's go back and write, expanding the left-hand side, we have a squared plus 2ab plus b squared is equal to, and 4 times 1/2 is 2ab plus c squared. Now notice that on both sides we have plus 2ab. So let's subtract 2ab from both sides. Minus 2ab minus 2ab from both sides gives us, well, what do you know? Let me change the color. I'll put it in green. It gives us, subtracting the 2ab from both sides, we get a squared plus b squared is equal to c squared. And we have proven the Pythagorean theorem. Now I'm not going to do this proof, but I put it in here because I want you to know it is exactly the same thinking that we just did for the first proof. Here I make 2 copies of our right triangle. And let's see, we could label this quickly. This is A, B, C. Here's the right angle, and here is the right angle, and we have the short side A, B, the longer leg, and the hypotenuse C. So we are going to add up the areas. We're going to find the area of the whole, the area of the trapezoid, and set it equal to the sum of the areas of its parts. So this is something you can find online, or we'll be working on it in class, so you won't need to do that. And we're going to do one other proof in class, which is done in our textbook, which is a slightly different way of proving the theorem. But this one and the last one are really exactly the same reasoning, so try to put those two together and see how they follow exactly the same plan. This proof was, by the way, thought of by President Garfield.